Hi, this is Barrett Givens, and in this video, I'm going to show that continuous functions preserve some kind of idea of being close, okay? So we sort of intuitively think of a point being in the closure of a set as meaning that the point is somehow close to the set. And so this theorem says that if you have a continuous function from a set X to a set Y, and you look at a subset A in your domain and a point X that's close to A by saying X is in the closure of A, if you apply F to sort of both sides of that, then you get that F of X is in the closure of F of A. And so if X is close to A, then F of X is close to F of A, is sort of the way to think about that. Let's go ahead and walk through the proof of this. So let's suppose that I have my space X and my space Y, and I have an A subset of X, and then its image, F of A. So all the points in A, every point that is in A, if I apply F to it, I'll land in F of A, okay, by the definition of F of A. And let's say I have a point X, which is near A, might be in A, might not, I don't know, but the point X is in the closure of A. And then let's look at the point F of X, and I just noticed that I have a little bit of an error right here that I thought I'd corrected. If X is in the closure of A, then F of X is in the closure of F of A. Okay, that might be wrong on my later slides too. Okay, so I want to show that F of X is in the closure of F of A. And the idea of the being in the closure, like how do I prove that a point is in the closure of a set, is that I have to, well, there's a lot of different ways I could do it, but one way is that I could look at a basic open neighborhood of my point F of X, and I could show that every open neighborhood of my point F of X touches F of A, that it intersects with F of A. So that's the strategy we're going to use. So let's just start by taking an open neighborhood U of F of X. So here's my open set U. It contains F of X, and I want to prove that U intersect F of A is not empty. So I want to find some element inside of this intersection right here. All right, but I don't know anything about U or F of A or anything. So what I'm going to do is I'm going to pull back up. So I'm going to take that set U, I'm going to look at its pre-image. So when I look at that set U and I look at its pre-image, well, U is open and F is continuous. So if I take an open set and I look at its pre-image under a continuous function, the definition of continuous is that this pre-image is open. So F inverse of U is open. Furthermore, F of X is in U, which means X is in F inverse of U, or pre-image. And so F inverse of U is an open set, and it also contains X. Now, up here on top, I know that F inverse of U is an open set, X is in it, but also X is in the closure of A. So any open set containing X has to intersect with A. Any open set containing X has to intersect with A. And that means that there has to be, let me fix this real quick. There has to be a point of some kind, some point that's in this intersection right here. Let's name that point B. There could be more than one point, but there has to be at least one. So we take this one point B. And now what I want to do is I want to ask, now if I apply F, where does B go when I come down back to down here? So B is inside of F inverse of U, which means F of B is in U. And also B is inside of A, which means F of B is in A. So F of B has to land in this region right here. F of B has to be an element of U, and F of B also has to be an element of F of A. And it doesn't really matter what the element is. The point is just that I found an element. I found something inside of U and F of A. I found something in that intersection, which means the intersection is not empty. And since U was an arbitrary open neighborhood of F of X, that means every open neighborhood of F of X intersects with F of A. And that is one of our characterizations of a point being in the closure of a set. And so that tells me that F of X is an element of the closure of F of A. Okay, thank you for listening.